Hello everyone. Today we're going to do a full review of AP Physics 2. So this exam, it's updated for the 2025 and beyond. So that means we're not going to be including fluids in this video. If you're taking the exam in 2024, check out the fluids from our AP Physics 1 review video. It's the last unit there because in 2025, fluids is going to be part of AP Physics 1 and not AP Physics 2. The link will be in the description. So here's our table of contents. First, we're going to do thermo, then electrostatics, then circuits, then magnetism, then geometric optics, then physical optics, and finally modern physics. Okay, first thermodynamics. So in a gas in a container, the atoms in the gas will collide with each other and the container's walls, and they exert forces when they collide. The collisions of the atoms, they all follow the conservation of momentum. And pressure exerted by a gas on a surface, think of that as just the sum of all the perpendicular components of forces exerted on a surface relative to its surface area. Pressure is equal to force over area, where force is the perpendicular force. Temperature is proportional to the average kinetic energy of the atoms in the container. So a higher temperature means that the kinetic energy of the atoms is higher. The gas molecules are moving faster. That's all temperature is. The root mean square speed, RMS, is the average speed for a gas particle. You find this by taking the average speed squared and then square rooting it, and that's because speed is a scalar. And you don't want the negative directions to get in the way. The average kinetic energy of a gas molecule is 3/2 times the Boltzmann constant, Kb, times by the temperature. And that's also just equal to 1/2 times by the average mass times by V RMS squared. So the Maxwell-Boltzmann distribution, it models the percent of particles on the y-axis as a function of the particle's molecular speed. So here we have three potential distributions of the Maxwell-Boltzmann curve. The first one has the highest speed. This is because, well, actually, my bad. The first one has the lowest average speed. These molecules are closest to the left side, closest to 0. Second one, second highest speed, second highest temperature, 2. And third one has the highest temperature, highest speed. Also note, because of conservation of mass, we're assuming all three of them have the same amount of and moles of gas molecules. The area under the curves of all of them have to be the same. So if it's 3, for example, the peak will be lower than if it's the first curve, for example. The ideal gas law. So there are certain assumptions that we use when we use the ideal gas law. First is that gas particles are in random motion. Second, the volume of the particle is negligible to the total volume occupied. Third, the atoms collide elastically. And we also assume that the forces only occur in collisions. The ideal gas law specifically states that PV is equal to nRT, where n is the number of moles, lowercase n is the number of moles, they're n kBt, where capital N is the number of atoms. We use Avogadro's number to convert between the lowercase n and the uppercase n. R and kb are constants that will be on the equation sheet. Thermal energy. Heating is just a transfer of energy into a system. This is because higher temperature indicates gas particles moving at a faster speed, and that means they have more kinetic energy. Cooling is just the opposite of heating, so that means energy out of a system. Conduction is the transfer of heat by physical contact. When you touch a hot stove, heat is being transferred to your skin, and that's why your skin will burn. Convection is hotter and less dense gases rising, while cooler gases sinking. Think of hot air rising above a fire. Radiation is energy given off by matter in the form of rays. The sun emits UV radiation, and that heats up the Earth's surface. So energy is always going to be transferred from systems with the high kinetic energy to those with the low kinetic energy. So therefore, in thermal equilibrium, that means no net energy will be transferred because the energy has nowhere to go since the net equilibrium is the same. The first law of thermal. So first, you need to know that ideal gases, it's impossible for them to have potential energies because there's no reference point. Therefore, the total internal energy of an ideal gas is just the total kinetic energy. Therefore, the internal energy is equal to 3 over 2 times by nRT is equal to 3 over 2 times nkBT. As we mentioned, is the total kinetic energy of a gas. The first law of thermo states that the change in internal energy of a system is just the energy transferred into or out of the system by work added to heat. So the final internal energy is equal to the initial internal energy plus work done plus heat added. Also note that work is equal to minus P times the change in volume. There's a minus sign because when the change in volume is negative, so the gas's volume is decreased, work is positive, and energy is transferred into the system. When a gas's volume is increased, work is negative. Think of the gas itself is pushing outward. So it's using energy and the gas is doing work to increase the volume. So it's going to have a lower final energy. Pressure volume graphs are used to represent these thermal processes. We use pressure volume graphs to represent these processes. So isotherms just refer to lines of constant temperature on the graph. The area under the curve of a pressure volume graph is just a net work done. This just makes intuitive sense. Also note that increasing volume is negative work. So we can use that on a thermograph to find out if the work is positive or negative. Isovolumetric curves refer to constant volume ones. Isothermal means constant temperature. And constant temperature means no change in internal energy. Isobaric is constant pressure. Adiabatic means no heat is transferred into or out of the system, but work can still be done. So internal energy can still technically change. Here are 3 graphs. The first one, upper left, this is just constant pressure graph, so isobaric. And we use these arrows to indicate whether which way the graph is going. For example, an arrow pointing to the right means volume's increasing, to the left, volume's decreasing. The next one, so upper right, this is an isovolumetric graph. This is because the volume is constant, so it's a vertical line. And again, the arrows mean the same thing. The final one, we showcase an adiabatic curve and an isothermal curve. This is what it'll look like. So an isothermal curve has a constant temperature. So P is inversely proportional to V, which is why the graph like that happens. And always note that an adiabatic curve is going to be steeper than an isothermal curve. This can be proved using calculus, but it's not covered in the scope of the class. And in an adiabatic system, the initial P1 times V1 doesn't have to equal the final P1 times V1 because work can still be done, so internal energy can be changed. Thermal conductivity. Specific heat is a material's intrinsic property, and that just depends on the atomic structure of the material. A material's specific heat just determines the energy required to change the material's temperature. Q is equal to M times by C times by the change in temperature. So the energy transferred by heating is the mass times by the specific heat times by the change in temperature. Thermal conductivity is an intrinsic property that also depends on atomic structure, but this one just determines the material's ability to conduct heat. A relevant equation is Q over the change in time, how much heat is transferred per time, is equal to K times by A times by change in T over L. K is just the thermal conductivity. L is the thickness of the material. and A is the cross-sectional area, and change in T is just the change in temperature. Capital change in T is the change in temperature. Lowercase change in T is the change in time. Second law of thermal. The second law states that the total entropy of a closed system will only increase or stay constant. And this will occur if the processes that the system undergoes are irreversible. However, for irreversible processes, entropy will always increase. Entropy, think of that as just the tendency of energy to spread. It can also be modeled as the number of microstates that are possible. A maximum entropy will always occur in thermal equilibrium. This is because there are so many more states that can occur. Think of it this way, right? The probability of rolling two dice with the sum of 6 is much higher than the probability of rolling two dice with the sum of 12 or 2. So the middle, where two systems are in thermal equilibrium, will have many more possible states. Closed systems spontaneously always move toward thermal equilibrium. And the entropy of an open system, it can decrease if the energy is transferred into or out of the system. Unit 2, electrostatics. Charge is a property of all matter, and it's positive or negative. The magnitude of charge on a proton or electron is just plus or minus c, and it's the smallest indivisible amount of charge. So that means all charge will be a multiple of that, E. And protons have a positive charge, electrons have a negative charge. In this course, we'll sometimes assume charges to be a point, so we'll ignore any mass that it has. Coulomb's law states that the electric force is equal to K times by Q1 times by Q2 over R squared. I put Q1 there, but in reality it's just Q2 because the force needs two charges. K is a constant and is equal to 1 over 4 pi times by E0, which is also a constant. Two objects with charges of the same sign repel each other, opposite signs attract each other. And these electric forces, they're responsible for certain macroscopic properties, like contact force. Normal friction and tension forces are all included in that. There are many comparisons that can be drawn between electrostatic and gravitational force. One thing to note is that electrostatic forces are attractive or repulsive. Gravitational forces are always attractive. The magnitude of gravitational force will usually tend to be smaller than the magnitude of electrostatic force, because the masses have to be huge for gravitational force to be large and have an impact. For example, the mass of Earth has a gravitational force. Furthermore, systems at a large scale will be electrically neutral or close to neutral. The gravitational forces dominate. Also note that the force equations for both gravitational and electrostatic forces are extremely similar. Electric permittivity is just a measure of how well a material gets polarized in the presence of a field. And polarization is just the rearrangement of electrons by an electric field. This will result in positive and negative charges being separated. For example, we know that positive charges attract negative charges and negative charges attract positive charges. If you bring a neutral, if it's a material with a high electric permittivity, and you bring a positive charge near it, the negative charges will go near that positive charge, and the positive charges will go to the other side. Free space has an electric permittivity of E0. And a material's permittivity, it depends on its composition, and it's just related to how easily electrons move in the material. In conductors, charge carriers move easily, while in insulators, charge carriers cannot move easily. Therefore, in conductor, the electric permittivity is high, while in insulators, it's not that high. Here's what I was talking about. Let's say there's this positive bar, and it's brought next to this electrically neutral circle. When this positive bar gets closer, all the negative charges will go to the side, close to the positive charge, and the positive charges will go to the other side, because it's still electrically neutral, so the net charge has to be 0. So note that the net charge of a system, it can change in the presence of another charge. This can be through contact. When two charged objects are in contact, the net charges will change of the system. So what we saw in the last slide is just induced charge separation. So the electrostatic force alters the charge distribution of the systems. Also note that total charge will always be conserved in a closed system. Charging of a system just involves the transfer of electrons to and from the system. Electric fields tend to originate from charged objects. E, the electric field, is equal to Fe over Q, and Q is the test charge experiencing the force. Electric fields are vector quantities, and field lines show a path the positive test charge would take. In electrostatic equilibrium, excess charge of a solid conductor is distributed on the conductor surface. An electric field within the conductor is zero. In electrostatic equilibrium, excess charge of an insulator is distributed through the interior and the surface. Therefore, the electric field within the insulator it may be non-zero. Here's an example of electric field lines. Essentially, they just follow a path a positive charge would take. So that means they point towards negative charges and point away from positive charges, as shown here. Electric potential energy. For a system of 2-point charges, electric potential energy of that system just equals the work required for an external force to bring the charges infinitely far away. So UE, electric potential energy, is equal to K times by Q1 times by Q2 over R. And again, K is equal to 1 over 4 pi times by E0. These equations will be on the equation sheet in the exam. Total electropotential energy is just the sum of all the electric potential energies of each pair of individual charges in the system. So you're just summing all the individual electric potential energies to find the total electric potential energy of a system. Electric potential is the electric potential energy per unit charge at a point. So therefore, the units will just be joules per coulomb. Electric potential due to many point charges can be determined by the sum of the individual electric potentials from each of the point charges. So again, you'll just use a net to find it. Electric potential difference between 2 points is the change in electric potential energy per unit charge when moved. And that's illustrated by the equation in the bottom. Change in V is equal to change in U over Q between 2 points. Conductors in electric contact will cause electrons to be redistributed. So the surfaces of the conductors will be at the same electric potential. Note that E, electric field, is equal to change in V over change in R between 2 points with 2 corresponding electric potentials and the distance between them. Equal potential isolines are just lines of equal electric potential in space. Electric field vectors point in the direction of high to low potential, the decreasing potential. Here are examples of equal potential isolines. So essentially, every circle is a point of equal potential energy in space. So for the diagram on the left, if there are 2 charges of the same sign, the isolines will connect. And it'll look something like that. But on the right, opposite signs, they will not connect. And there will be a divide between them. Capacitors. Parallel plate capacitors have 2 separated conducting surfaces, and they all hold equal amounts of charge and have opposite signs. So it'll just have one side which is positively charged, separated by a distance, to another side which is negatively charged. Capacitance is the magnitude of charge that can be stored on each plate to the electric potential difference created by the charges stored. So C is equal to Q over change in V. Capacitance depends on the capacitor's material. So C is also equal to K times by E0 times by A over D. So EC is equal to Q over K times by E0 times by A. That's the electric potential energy of a capacitor. No, sorry. That's the electric field created by a capacitor. Think of the electric potential energy a capacitor stores as equal to the work needed by an external force to separate the charge on the capacitor. So UC is equal to 1/2 times by Q times by the change in V. The change in U in the electric potential energy is equal to Q times by the change in V. The movement of a charged object between 2 points with different electric potentials will cause a change in the object's kinetic energy. This just makes sense, right? Because think of the electric potential that's doing work on that object. And here we draw a diagram of a parallel plate capacitor, and we show the electric field lines. So note how they're all straight, except on the end. On the end, it's going to be fringing. It's not going to be exactly a straight path because it's at the end. And here are some units that we didn't go over in the slides, but you all should know. Unit of electric charge is Coulomb, electric force, newtons, electric field, newtons per Coulomb, electric potential energy, volts, capacitance, farad. Unit 3, circuits. Electric current is the rate at which charge passes through a cross-sectional area of a wire. I is equal to change in Q over T, the change in charge over time. Electric charge moves in a circuit in response to a potential difference. And that potential difference is referred to the EMF, electromotive force. If the current is 0 in a section of wire, the net motion of charge carriers is also going to be 0, by definition. Also note that current is not a vector, but it has direction. In circuits, we choose conventional current to be the direction in which positive charge would move. Even though in common circuits, in real life circuits, current is always due to the movement of negative charge carriers. And here are the basics of circuits. The circuits are composed of electrical loops where charge can flow through, and they always flow through closed loops and never open loops. Furthermore, more electric potential differences are needed for current to flow. Here we show some symbols and what they mean. So there's the battery, bulb, switch, capacitor, resistor, ammeter, and voltmeter. Ohm's law. Ohm's law is just the resistance to which an object opposes current. R resistance is equal to PL over A, where P is the resistivity of the material and it depends on its molecular structure. Resistivity can increase with temperature. Ohm's law states that I is equal to change in V, change in potential difference over R. Also note that ohmic materials will always have a constant resistance regardless of the current or temperature. Electric power is the rate at which energy is transferred, converted, or dissipated by a circuit element. Electric power of a bulb will increase and can be considered as just brightness. Power is equal to I times by the change in V is equal to I squared times by R and is equal to change in V squared over R. Okay, here are the important stuff for DC currents, which are just direct current circuits. The circuit elements will either be connected in series or parallel, or both. In a series circuit, all the current will pass through one path, so therefore the current must be the same in each path. In a parallel circuit, the current splits across different paths. but the total potential difference across each path must be the same. A collection of resistors in a circuit can be used and analyzed as if it were just one resistor through the R equivalent equation. In a series circuit, that equivalent resistance is the sum of all the individual resistances. But in a parallel circuit, 1 over R equivalent is equal to the sum of 1 over all the resistances. So 1 over R1 plus 1 over R2 and so on, that's equal to 1 over R equivalent. In a series circuit, because of the equation, you can prove it, more resistors mean the higher R equivalent. But in a parallel circuit, more resistors means the lower R equivalent. Ideal batteries and wires always have negligible resistance. Continuing on DC currents, in a non-ideal battery, we'll treat the internal resistance as another resistor. So change in V, the voltage of the circuit, or the change in potential difference of the circuit, is just E, the electromotive force, minus I times by R, where R is the internal resistance. Ammeters will measure the current at a certain point in a circuit, and they will ideally have no resistance. While voltmeters will measure a potential difference between 2 points in the circuit. This makes sense, right? Because for a difference, you need to measure between 2 points. Kirchhoff's rules. Kirchhoff's loop rule is due to the conservation of energy. And that just states that the sum of potential differences across all circuit elements must be equal to 0. This is why in parallel circuits, no matter the path, the potential difference along each path must be the same. Electric potential in a circuit can be represented by a graph. Kirchhoff's junction rule is due to the conservation of charge. Junction rule states that the total amount of charge entering a junction per unit time must equal the total amount of charge exiting the junction. That's just saying total charge is conserved. So here's the diagram illustrating what I mean. So this upper diagram is a circuit in series. And on the right, I have a graph of the potential difference as a function of distance. So initially, across the battery at point 0, there's a high potential difference. Then as you go to resistor 1, the potential difference drops because of that resistor. Then as you go to resistor 2, the potential difference has to drop to 0 because the net voltage, the net potential difference has to be equal to 0 across all elements. And yeah, it has to be balanced. This bottom circuit, it represents Kirchhoff's loop rule. So this current of 3 amperes is going to split between both of these parallel loops. 2 amps will go to that resistor, and 1 amp will go to the top component. Yeah, and in general, parallel circuits, more current will be distributed to the resistor with the lower resistance. This is because the potential difference has to be constant. So the path with the lowest equivalent resistance, more current will be distributed there. RC circuits, resistor capacitor circuits. So capacitors can be in circuits, and a collection of capacitors can be treated as a single capacitor with an equivalent capacitance. For capacitors in series, 1 over C equivalent is equal to the sum of 1 over all Ci. And C equivalent is equal to the sum of all individual capacitances for capacitors in parallel. So it's the opposite for DC circuits with equivalent resistances. Each capacitor in series must have the same magnitude of charge on each plate. The time constant for an RC circuit is a measure of how fast the capacitor will charge or discharge. So the time constant, T, is equal to R equivalent times by C equivalent, capacitance equivalent times by equivalent resistance. For a charging capacitor, the time constant is the time required for the capacitor to reach 63% of its final asymptotic value from zero. For a discharging capacitor, the time constant is the time required for the capacitor to reach 37% of its initial, which is the fully charged value. So capacitors take time to charge, as shown by the time constant. And a fully charged capacitor will have zero current flowing through that branch, because it just can't accept any more charge. So usually a capacitor will discharge after. When a capacitor discharges, the charge on its plates and energy stored will decrease. And we can use steady state conditions to describe a capacitor if it has been charging or discharging for a long time. Unit 4, magnetism. Magnetic fields are vector fields used to determine magnetic forces on moving charges, currents, or materials. Magnetic fields are always produced by dipoles and never non-dipoles. Dipoles are just a pair of equal and opposite electric charges or magnetic poles. So we all know magnets, right? They'll have a north and south polarity on two opposite sides. Magnetic fields are vectors, and you can use vector field maps to represent them. And magnetic dipoles result from rotational motion of electric charges in magnets. But just electron motion. Permanent magnetism are properties that result from alignment of magnetic dipoles. A north pole will always exist with the south pole. So even if you break the magnet in half, there will still be a north and south pole in both of those. Continuing on magnetic fields. Same polarity poles will repel, and opposite polarity poles will attract. Note, this is pretty similar to electric charges, which makes sense. Magnitude of a magnetic field from a dipole will decrease with increasing distance. This also makes sense. Just as electric force decreases with increasing distance. A magnetic dipole placed in a magnetic field will align with the magnetic field. Ferromagnetic materials like iron and nickel, they tend to be permanently magnetized by an external field that causes alignment of atomic magnetic dipoles. Paramagnetic fields like aluminum and titanium interact weakly with an external magnetic field. So they don't remain aligned after the external field is removed. But most materials tend to be diamagnetic. So that means they align in the opposite direction at the magnetic field. Magnetic permeability is the amount of magnetization in response to an external field. Note that free space has a magnetic permeability of mu0. Matter permeability depends on its composition and varies on internal factors like temperature and also the strength of the field applied. Moving charges can produce magnetic fields. Magnetic field at a point created by a moving charge just depends on the charge's velocity and the distance between the point and the object. And we can use the right-hand rule to determine the direction of magnetic fields. And yeah. Point the thumb in the direction of the velocity if the charge is positive, and point it in the opposite direction if the charge is negative, if charge flowing is negative. And then you can curl your fingers. Then you'll know if the magnetic field is clockwise or counterclockwise. Magnetic field is a max when the velocity vector and position vector are perpendicular. So we can use this equation to describe magnetic force. QVB sine theta. The sine theta makes sense because when theta is 90, sine of theta will be 1. And we also use the right-hand rule to determine the direction of magnetic force. So we point the finger in the direction of velocity, middle finger in the direction of magnetic field, and the thumb will then point to the direction of force. Note that charged objects will experience forces separately from both magnetic and electric fields if they are in the presence of both. Current carrying wires produce magnetic fields, as charge is flowing by definition of a current. Magnetic fields for a current carrying wire are tangent to concentric circles on the wire. Yeah, so they'll just be tangent to the circle. So this diagram represents what I mean. If the charge is moving upwards, we can just use the right-hand rule, point our finger upwards and curl our fingers, point our thumb upwards and curl our fingers in the direction, and that'll be the direction of the magnetic field. And it's going to be in a circle, so that's why it's going to be tangent. Current carrying wires also experience forces from magnetic fields. That FB will be I times by L times by B sine theta. Note that X on a diagram means going into the board, O means out of the board. We use these conventions. As in magnetism, we use all three dimensions to describe force, velocity, and field. Electromagnetic induction and Faraday's law. First, we must describe what magnetic flux is. Magnetic flux is just how much of a component of a magnetic field goes through a certain cross-sectional area. Look at this diagram. Let's say that circle is the cross-sectional area. Magnetic flux is how much of that magnetic field goes through that area. Magnetic flux is equal to B times by A cosine theta, where A is the area, and theta is the angle between B and the normal to the area. Faraday's law states that E, the electromotive force, is equal to the change in flux over time. We use Lenz's law to determine the direction of an induced EMF from a changing magnetic flux. So essentially, when magnetic flux changes, there will be an induced EMF. And that induced EMF can be used to power a circuit. So essentially, E is equal to the minus change in flux over time, which is equal to the minus change in B times by A cosine theta over change in time. So essentially, the minus sign indicates that induced EMF generates a current that creates a magnetic field, and that magnetic field opposes the change in magnetic flux. So that magnetic field has to create a force that opposes the change in flux. So if the flux is increasing, then find the magnetic field that will cause the force to make the flux decreasing. And again, we have to use the right-hand rule to determine directions of current, EMF, and flux. Unit 5, Geometric Optics. So light rays are EM waves, electromagnetic waves, that follow a straight line path where the light energy travels. In geometrical optics, essentially, light has both particle and wave-like properties. So we just treat light as like a ray, and we ignore the wave properties. However, later we'll go over how light does behave like a wave. Ray diagrams show the path of light in matter interactions. And the law of reflection just states that the angle between the incident ray and the normal is equal to the angle of the reflected ray and the normal. Diffuse reflection means that the reflected light will be reflected in different directions. And this is common when light is reflected by a rough surface. Specular reflection is when light is reflected by a smooth surface, which results in uniform reflection. So here's a diagram showing what I mean. So I drew the normal there. And when an incident light ray is shown, it'll make an angle with the normal. And then the reflected ray usually reflects at the same angle as the first one. So mirrors actually form images through light. Converging or concave mirrors, they reflect light towards a common location, and that's known as the focal point. Diverging or convex mirrors, they reflect light such that it appears to have originated from a common location behind the mirror, and that's known as the focal point in this context. And we use ray diagrams to determine the location of the image. In the ray diagrams, we draw 3 rays. The first ray goes from the source horizontally. It hits the mirror and reflects through the focal point. One ray goes directly through the focal point, and then it reflects horizontally. And the final ray strikes the center of the mirror, and by the angle of incident and reflection, it reflects at the same angle. We refer to real images that are formed when the light rays intersect at a common point, and virtual images are formed when light rays diverge. So they appear to have originated from a common point, but they don't actually intersect at a common point. So this is an equation that describes the location of the image, the object, and the focal length. 1 over s psi plus 1 over s0 is equal to 1 over f. And magnification is described by how large the resulting image is, the height of it is compared, or the length, or the distance, I mean. So hi over h0 is equal to si over s0, and that's the magnification. We use ray diagrams to determine whether images formed are inverted, straight, virtual, real, enlarged, reduced, or the same size. Here's an example of what I mean. These are 2 ray diagrams. The first one is for a concave mirror, and essentially the image is straight up. One ray is drawn horizontal straight, and it reflects through the focal point. Another ray goes through the focal point initially, and it reflects horizontally. And the third ray goes through the center and reflects at the angle of incident, the first angle of incident. And the resulting image formed is inverted, but it's real because they all intersect at one point. The second mirror is a convex or diverging mirror. This is the case because the circular side is away from the image. So again, the same thing holds. One ray is horizontal and it's supposed to go to the focal point. So we draw both the lines because it's going to be diverging. The second ray goes through the center. And again, we draw both the lines because for diverging mirrors, it'll appear to have originated at a certain point. That's why we draw both the actual reflected lines and the lines that it appears to have come from. And finally, we draw the last one, which is supposed to go through the focal point on the other side, but it reflects horizontally. And yeah, as you can see, this image is virtual and upright. It's virtual because it's on the other side of the mirror. It appears to have come from that side, and it's upright. Refraction refers to the change in direction of a light ray as the ray passes through different mediums. The speed of the light ray will change as it enters a new medium. And the index of refraction, C over V, where V is the speed of the light in the new medium, is used to compare how fast light travels in different mediums. Snell's law states that n1 sine theta 1 is equal to n2 sine theta 2, where n1 and n2 are the respective indices of refraction, and theta 1 and theta 2 are the angles the light ray makes with the normal. Therefore, by this equation, when the light ray travels from medium with the higher n to medium with the lower n, the ray refracts away from the normal, and the opposite will be true as well. Total internal reflection of light occurs beyond a critical angle. So when the angle is greater than the inverse sine of n2 over n1, total internal reflection occurs. So that will be a full reflection of light back into the starting medium, and nothing will refract into the next medium. And it'll only occur if the incident rate is beyond the critical angle. So here's just an example of reflection and refraction. So the index of refraction of water is greater than that of air. The light ray enters the water, it refracts towards the normal, and then exits the water and refracts at the same angle as before. Converging or convex lenses converge light rays to a common location on the transmitted lens side. Diverging or concave lenses diverge rays, making it seem like the light originated from a point on the incident side of the lens. This is sort of the opposite as mirrors. Converging mirrors are concave mirrors, but converging lenses are convex lenses. So real images will be formed when light intersects at a common point. And again, virtual images will be formed when light rays diverge, making it seem like they originated from a common point. The thin lens equation, 1 over SI plus 1 over S0 is equal to 1 over F, is similar to the mirror equation. And yeah, they both describe the same thing. The only difference is real mirror images will form on the same side, while real lens images will form on the other transmitted side. And again, magnification has the same equation. With this one, we also use ray diagrams to determine location, type, size, and orientation of images. The ray parallel to the principal axis goes through the focal point on the other side. The ray that passes through the center remains unchanged, and the ray that passes through the focal point goes parallel to the principal axis. So the top one is an example of a converging lens or a convex lens. As you can see, one ray goes through the focal point and then goes horizontally on the other side. The other ray goes through the center and just continues. And the third ray, the top ray, it goes horizontal and then reflects goes through the focal point on the other side, forming an image on the other side. And it's real because it's on the other side. And in this case, it's inverted. The second example is from a diverging lens. So in the second example, one ray goes horizontal and it's set to reflect at the focal point or away from the focal point in this case. And so we draw both the lines because it will appear to have originated from some point. Then we draw the second line. The middle line is supposed to reach the second focal point on the other side. And then it will just reflect horizontally after. And the third line at the bottom that we drew, it just goes through the center and it doesn't change. And there we got our next image height as shown by the line I drew. This image is real. I mean, not real, it's virtual and it's straight side up, so it's not inverted. Unit 6, physical optics. The properties of waves. Waves are modeled as a periodic disturbance with a defined wavelength and frequency. They can transfer energy between two locations. Mechanical waves, like earthquakes, they require a medium to propagate. Like earthquakes use the land. While EM waves, electromagnetic waves, like UV light, they do not require a medium to propagate. The speed of a wave through a medium depends on the wave type and its properties. The speed of EM waves in a vacuum is c is equal to 3 times 10 to the 8 meters per second. The speed of a wave pulse along a string is the square root of the tangent force over the mass over the length. The speed of sound waves increase with the temperature in the medium. Transverse rays refer to rays where the disturbance is perpendicular to the propagation of the wave. But in longitudinal waves, direction of disturbance will be parallel to the direction of propagation. Sound waves are longitudinal, but most other waves are transverse. Think of a sine curve as a transverse wave. The amplitude refers to the max displacement of a wave from equilibrium. And the energy and loudness increases with increasing amplitudes. Periodic waves have regular repetitions, which are described by period and frequency. Period is just the time to complete one full oscillation. Frequency is 1 over the period. which is just the rate at which the wave repeats. The wave's amplitude does not depend on the frequency or period. And the energy of a wave is directly proportional to its frequency. The wavelength is the distance between two consecutive points on the wave. So the distance between two troughs or two crests. So two of the top ones or two of the bottommost points. Sinusoidal waves are described by these two functions, or you could replace cosine with sine. So it's just a cosine omega t or a cosine 2 pi ft. For periodic waves, wavelength is equal to speed over frequency. Here's an example of a wave, and this can be modeled by a sine curve. So the amplitude is just the highest point, and it'll be constant. The wavelength is the distance between two of the same points, as shown by the bottom. So waves traveling between two mediums, they can be transmitted or reflected. But that depends on the properties of the boundary separating the media. Reflected waves will be inverted if the transmitted wave traveled into a medium where the speed of the wave decreases. This is really important. But a reflected wave will not be inverted if the transmitted wave traveled into a medium where the speed of the wave increases. The frequency of the wave will remain the same, no matter what. Transverse waves can be polarized and can oscillate in a single plane. However, polarization may result in a reduction of wave intensity. Wave intensity is just the power transferred per unit area, or the average power per unit area over one period of the wave. And also note, this only applies to transverse waves. Longitudinal waves cannot be polarized. So EM waves, electromagnetic waves, they consist of oscillating electric and magnetic fields that are mutually perpendicular. EM waves are transverse because the oscillations of electric and magnetic fields are perpendicular to the direction of propagation. And EM waves do not need a medium to propagate through. EM waves are characterized by wavelength. The higher wavelength means lower energy and lower frequency. And here's some examples of common EM waves you should know. And they're all in order of decreasing wavelength. So highest to lowest wavelength, or lowest to highest energy level. Radio waves, microwaves, infrared, visible, UV, X-rays, and gamma rays. And visible EM waves can be further broken into categories of color. Think of the rainbow, Roy G. Biv. And that's actually the order from high to low wavelength, or low to high energy level, or low to high frequency. The Doppler effect describes the relationship between rest frequency, observed frequency, and relative velocity between the source and the observer. So a greater relative velocity will just mean a greater difference between the observed and rest frequencies. This is pretty intuitive. So a wave source moving at the same velocity as the observed frequency is equal to the rest frequency. A wave source moving toward an observer, the observed frequency is greater than the rest frequency. And a wave source moving away from an observer, the observed frequency is less than the rest frequency. Wave interference is just the interaction of two or more waves. Waves tend to overlap rather than bouncing off each other. And when two or more waves overlap, this is called superposition. So we superposition the individual displacements by adding them together to find the resulting displacement. Constructive interference refers to when the wave pulses are in the same direction, so it increases. Destructive interference is when the wave pulses are in opposite directions, so it detracts from the total wavelength. Waves with different frequencies can be in phase or out of phase at locations. So the superposition wave will have period amplitude changes. Beat frequency is the difference in frequencies of two waves, and tuning forks demonstrate beat frequencies. Standing waves result from interference between two waves that are confined to a region and are traveling in opposite directions. Nodes are points where the amplitude is zero, and antinodes are where the amplitude is always a maximum. The fundamental or first harmonic in a standing wave is the wave with the longest wavelength, The second harmonic is the wave with the second longest wavelength, and so on. Diffraction refers to the spreading of a wave through an opening. And diffraction will be most pronounced and greatest when the opening of the hole, the opening size, is comparable to the wavelength of the wave. The diffraction of many waves through a single opening leads to many interference patterns. And constructive and destructive interference results as results as an effect. So this causes bright and dark bands on the screen. The distance is just equal to a sine theta between corresponding bright spots and dark spots. For small angles where theta is less than 10 degrees, we use this equation. A times by the minimum y over L is equal to m times the wavelength. Young's double slit experiment discovered interference patterns by light, and this basically indicated that light does have wave properties. The main difference between double slit and single slit is that in double slits, you will get a dark spot at the location where you got a bright spot in the single slit. Thin film interference. Phase change of a reflected ray depends on the indices of refraction of materials which the ray interacts with. A phase change of 180 degrees occurs when a light ray is reflected from a medium with the greater index of refraction than the medium through which the ray is traveling. No phase change will occur when a light ray is reflected from a medium with the lower index of refraction than the medium through which the ray is traveling. And the wave phase will not change when it is refracted. Thin film interference occurs when light interacts with the medium whose thickness is comparable to the light's wavelength. And the light waves reflect off top and bottom surfaces of a thin film. Thin film interference occurs through the color variations, and this can be shown in soap bubbles and oil films. Unit 7, Modern Physics. Quantum theory was developed to explain observations of matter and energy that could not be explained using classical mechanics. And these topics include blackbody radiation, the photoelectric effect, atomic spectra, and so on. In quantum theory, fundamental particles exhibit particle and wave-like behavior. And light is modeled both as a wave and as discrete particles called photons. Photons are massless and neutral particles, and energy is proportional to the photon's frequency. That energy, E, is equal to h times by f. The wavelength is equal to c over f. The speed of a photon depends on the medium it travels through, but in free space, c will be equal to 3 times by 10 to the 8 meters per second. The speed of a photon through a medium is inversely proportional to the index of refraction in that medium. The de Broglie wavelength is equal to h over p, where p is the momentum. So in quantum theory, the wavelength of a particle will decrease with higher momenta. The particles moving faster have less wave-like properties. This is a very important topic that you need to understand. The Bohr model. Atoms will consist of a small positively charged nucleus surrounded by negatively charged electrons. And the nucleus contains protons and neutrons. Ions are atoms that have a non-zero net charge, and each unique element has a unique number of protons. These are just basics of chemistry that you probably already learned. Isotopes will be atoms of the same element with different number of neutrons, and the mass of an atom is just dependent on the protons plus the neutrons in the nucleus. Electrons are modeled as moving around the nucleus in circular orbits determined by the electron's charge and mass and the electric force. And these are two equations that we went over, but you should know. Electric force is equal to that. We went over this in Unit 4. And the net force of an electron can be just modeled by circular motion, as the electron will be orbiting. And electrons have specific allowed energy states. The electron is quantized. It can only exist in certain energy states and not others. So energy transfer can occur when photons are absorbed or emitted by atoms. And this is modeled as a system of a nucleus and electron. A photon can only be observed or emitted if there's an exact difference between two atomic energy states. So the difference of the photon energy must be the exact difference between two atomic energy states. Absorbing photons allows the atom to go into a higher energy state, while emitting photons will allow an excited atom to move to a lower energy state. Electrons will jump or go back down because of photons. They'll jump to higher energy levels, or an atom will emit an electron, or an atom's electron will go to a lower energy level and emit a photon. Binding energy refers to the energy required to remove an electron from an atom. And this removing an electron from an atom will turn the atom into an ion. It's also called the ionization energy. So matter will spontaneously convert some of its internal thermal energy into electromagnetic energy. Black bodies are idealized models of matter that just absorb all types of radiation. Like in general, the color black will absorb all types of radiation. A black body emits continuous spectra, and that depends on the body's temperature. The peak wavelength emitted by a black body decreases with increasing temperature. The max wavelength is equal to B over T. B is the constant of proportionality, and T is the temperature. So yeah, decreases with increasing temperature. The rate at which energy is emitted, the power of a black body, is proportional to the surface area of the body and the temperature raised to the fourth power. And that's just described by this equation. P is equal to A times by the Stefan-Boltzmann constant times by the temperature to the power of 4. The photoelectric effect. This just describes the emission of electrons when electromagnetic radiation, I don't know why I put RM, it should be EM. EM radiation is incident on a material. The threshold frequency is the minimum frequency of incident light required for electron emission. And the work function of a material is the minimum energy required to emit an electron from atoms in the material. So the max kinetic energy is equal to HF, the energy of the photon, minus the work function. This is just normal conservation of energy. The photon will come in with some energy. It uses some of the energy for the work function, and the rest of the energy is transferred to the to the electron. And yeah, the electron will fly out. Compton scattering. The compton scattering just refers to when a photon interacts with the free electron. The Compton effect is when a photon that emerges from the interaction has a lower energy level and a longer wavelength than the incoming photon. Compton scattering just shows evidence that light is a collection of discrete quantized energy packets called photons. So we just treat light as a photon, another particle, and apply conservation of energy and momentum to the collision between the photon and electron. The energy is just equal to HF of the photon. The wavelength is equal to H over P. And the change in wavelength is equal to H times by 1 minus cosine theta. We'll go over the exact theta in the next slide. Divided by the mass of the electron times by c, the speed of light. So here's a diagram showing Compton scattering. This photon is, it hits an electron, and then the electron will move upwards, and the photon moves downwards, and that's the angle theta between the initial photon and the final angle of the photon. And that's the theta used in the equation for the change in wavelength. Fission, fusion, and nuclear decay. The strong force is one of the 4 fundamental forces, and it's exerted at the nuclear scale. It dominates the interactions of nucleons. The nuclear reactions are constrained by the conservation law and the conservation of nucleon number. In nuclear reactions, the mass energy equivalence allows mass and energy to be exchanged. So this just means E is equal to mc squared. The energy mass can be converted to energy. Energy can be released in nuclear processes as kinetic energy of the product or as photons. And nuclear fission just occurs when two or more smaller nuclei, form a larger nucleus. Nuclear fission occurs when the nucleus of an atom splits into two or more smaller nuclei. Radioactive decay is the spontaneous transformation of a nucleus into one or more nuclei. And the half-life is just the time it takes for half the initial number of radioactive nuclei to spontaneously decay. That's pretty self-explanatory. The decay constant is referred to as log, is just calculated by the log of 2 over the half-life. And we can use the decay constant to find how long it'll take for an atom to decay by a certain amount. So the log of n, the final, over n0, the initial, is equal to minus decay constant times by the time it'll take. We can use this for many purposes. Like if we have 3 of the 4, we can find, if we have 2 of the 3, or 3 of the 4, sorry, if we have 3 of the 4 variables, we can find the other variable. Types of radioactive decay. Alpha particles are helium nucleuses. So that just means they have 2 neutrons and 2 protons. The symbol is He2+, or an alpha. Neutrinos and antineutrinos are subatomic particles with no electric charge and negligible mass. And they're symbolized by V. So neutrinos are symbolized by V. Antineutrinos are symbolized by a V with a slash or a dash on the top of the V. Neutrinos and antineutrinos interact with matter by the weak gravitational force. Positrons or anti-electrons are just subatomic particles that have an electric charge opposite that of an electron, but they still have an electron's mass. And they're symbolized by E+ or B+. In every nuclear decay, the nuclear number, the lepton number is just the electrons plus neutrinos, and nuclear number is just the number of protons plus neutrons, and the charge are all conserved. Alpha decay is when a nucleus ejects an alpha particle. Beta minus decay is when a neutron changes to a proton by emitting an electron and an antineutrino. Beta plus decay is when a proton changes to a neutron by emitting a positron and neutrino. And gamma decay is when a nucleus has already gone alpha or beta decay, and the excited nucleus decays to a lower energy state by emitting a photon. You should know all 4 of these decays pretty well. And yeah, that's it. That's the full review of AP Physics 2. Some of the concepts are pretty challenging, but the last maybe 2 units are mainly conceptual. So you just need to understand how it works. And if you have any questions, please let us know in the comments. This video took a while to make, so a subscribe and a like would greatly be appreciated. Thanks for listening and best of luck.